start with observability in state space, that is part 2. In this we will study detectability, that is partially observable system, then condition of observability in the presence of pole zero cancellations, then principle of duality. Now we start with the detectability, that is partially observable system. In earlier time we have seen a general example of understanding of controllability, observability. Again we have seen stabilizability, which is called partially controllable system. Here also we have to see a partially observable system. What is meant by partially observable system? Let us say there are 10 students, they are going from, let us say from IIT Roorkee, let us say 10 student. So each student will be represented by state. So x1, x2, x3, let us say x10. These are 10 students and they are going from for industrial trip, let us say they are going to Delhi, and in Delhi there is some industry and they have to go. So all the states which are here, they have to reach to Delhi. So it is found that out of this all the states, x1, x3 up to x10. So these 9 state has been observed, whereas this x2 state it is not found here. So this x2 is absent. So here we found that if any of the state is missing, system is unobservable. But here we found that the state x2 which is absent, or the student which has to reach to industry, he is not found, but what we have found that he is somewhere at a safer locations, that is he is safe, there is no as such issue. So if that instructor who is been travel with the student, he is found that that particular student he has to reach to the company or industry, but he has not reached, but somewhere he is safe and there is no as such worry. So what happen? The teacher what will do? He will take 9 students to industry and leaving only that particular state. So in that case we call as, it is called a partially observed system. That means all 10 has to reach, but some problem he could not reach, but still we can say that system is an observable, but here it is called as partially observable system. So this partially observable system, it is called as detectability. So how to define this? The system is partially observable when unobservable modes are stable and observable modes are unstable. Now we will see through an example. Suppose write x dot, that is ax plus b into u, x dot equal to ax plus bu. Now here this A matrix is represented by -1, 0, 0, 2, x plus 1, 1, u, that is here B, this B matrix. So x dot equal to -1, 0, 0 minus 2x plus 1, 1 into u. So here this is A matrix. In A matrix, -1 and 2 are the diagonal elements, and 1, 1, this is a B matrix. So we will find that this particular system is controllable because here elements are 1, 1. Now we think about the observability. Now here output of this system we can write down as 0, 1 into x. Now, this is a C matrix. We have seen that controllability depends upon A and B, whereas observability depends upon A, this A matrix, and this is C matrix. Now, we will find that corresponding to this -1, that is a stable mode, but this part is shown unobservable, whereas this 2 is unstable, but it shows that 1 as a observable mode. So, when this is the case, so this is called as a partially observable system. So, this 0 is showing here, it is unobservable mode, whereas this 1 indicate observable mode. Therefore, in a real practice we can consider this type of system also. Now, the condition of observability in the presence of pole 0 cancellations. When we are considering the system, that is in terms of x dot equal to ax plus bu, y equals to cx plus du, and here we are using either Kalman test or Gilbert test to check the observability of the system. Let us say if the system is not observable, then if you take that particular system, convert into transfer function, can it possible that there is pole 0 cancellations? Now, we will see this effect. Suppose if you write A matrix as this A is equal to 0 1 0 0 0 1 and here -90 -63 -14, this is A matrix. Now, here we write a B matrix as 0 0 1 and C matrix as 12 7 1. So, state space model involved ABC. So, we have written A, B and C. Now, we have to check the observability of the system. So, how do you check the observability? So, for observability, this Q observability, that is C transpose A transpose C transpose A transpose square C transpose. So, we have written A C transpose, A transpose C transpose, A transpose square into C transpose. So, it is this 2 means n minus 1. So, the order is 3. So, we are written 2. So, n minus 1, 3 minus 1, that is equal to 2. So, C transpose, A transpose, C transpose, A transpose square, C transpose. So, this is basically a Kalman test. Now, what is C? C is 1271. So, we have to take C transpose. Then A is this one. So, we have to take A transpose and multiply by C transpose, and similarly this one. So, after doing multiplication here, we will get the observability matrix as 12 7 1 12 7 1. Now, if you multiply A transpose and C transpose, you will get -90 -51 -7. Here we will get 630 351 and this 47. So, this observability matrix we determined. Now, if you take the determinant of this, so the determinant of this observability matrix, so we will find that if you take the determinant of this, it comes 0. So, this particular system, it is unobservable. Now this system is unobservable. Now what we can do, we have ABC. Now we convert this given state space model into transfer function. So we will find that the transfer function of this system is represented by s square plus 7s plus 12 divided by s cube plus 14 square plus 63s plus 90. If you just see here, this is A matrix. So this is in a companion form or a controllable canonical form, because 0 1 0 0 1 minus 90 minus 60 minus 43 and 0 0 1. So this can be easily written in this form. We have already seen this, how to represent it. So this transformation we have got, but just looking after this transformation, we do not know whether there is a pole 0 cancellation or not. So in order to know whether these pole 0 cancellations, we have to solve this equation and this equation. That is, we have to calculate the roots of numerator as well as the roots of the denominator. So the roots of the numerator here, s plus 3, s plus 4. So if you solve it, s cube s square plus 7s plus 12. Now about this denominator. So denominator is nothing but the roots of the denominators are s plus 3, s plus 5, s plus 6. So we will find that s plus 3 and s plus 3 is common, and here we can cancel it, and remaining is s plus 4 divided by s plus 5 and s plus 6. So we will find that this s plus 3 has been cancelled. So here system is unobservable. So this observability of the system has been tested by using transfer function. This can be tested by using this Kalman form. So any of them can be used, but here we will find that if there is a pole 0 cancellation, system itself is unobservable, and here this s plus 3 and s plus 3, this particular state is not available for the measurement, because in a state space design or actual practice, we had to design a controller. So the controller design is only possible when states are available. So here we will find that for this particular plant, the state is not available, therefore the controller design cannot be possible. So how to design a controller and all these issues we will see later on, but for time being we will find that this particular state is not exist, it is cancelled, and therefore our system we can say call as unobservable system. Now about the principle of duality. So what is meant by principle of duality? So it is said that if the system S1 is completely state controllable, we have seen what is meant by controllability. So if it is completely state controllable, if and only if the system S2 is completely observable, that is, if you take one system S1 and take the dual of each, it found that they are related, that is S1 is completely state controllable, S2 is completely observable. Again the reverse case, if system S1 is completely observable, if and only if this S2 is completely state controllable, that means initially there are controllability, then observability, then here observability and controllability, they are related to each other. Now we will see how they are related. We have seen the different types of form, companion form, canonical form. In this different companion forms, we have seen the controllable canonical form, then observable canonical form. Now we will see this form and how they are related in case of controllability as well as in case of observability. So here first of all we write one system S1. S1 is the one system as we are written here S1. So that is why I written S1 here. For S1 we have to take one model. Suppose this model is represented by x dot equal to ax plus bu and y equal to cx. This is system S1, this is S1. A is the system matrix, B is the input, C is the output matrix. And now we assume that this particular system, it is in controllable canonical form. And now the same system we can write in terms of observable canonical form. So when we write observable canonical form, we take a different states. Let us say we have a system S2 like this, and this S2 written as say Z dot to A transpose Z plus here the B in this case is nothing but the transpose of C, that is C transpose. So vector we can take, instead of x we can take V, and output let us say N can be written as B transpose into Z. That means here this B, instead of B we got C, and instead of C we got B. Now there are system S1 and system S2. So here we can take a different inputs, different outputs, but now assume that the inputs are for S1, inputs for S2, but the thing is that this A and A transpose, C is coming as C transpose and B is coming as B transpose. Now what we will do, we will check the controllability and observability for this system, also the controllability and observability of this system S2, S1 and S2. Now for this system S1, the state controllability that is say QC. So here controllability by Kalman test we can write down as B AB and this process repeated A raised to n minus 1 B. That is state controllability for S1. Then observability for this system S1. So observability that is Q0, Q naught equal to, so observability means we have to write C transpose A transpose C transpose, and this process repeated we can write down as A transpose n minus 1 C transpose. So now this the controllability and observability equation for this particular system, this part, these are related. Now coming to system 2. So now for system S2, now we write the equation as same equation Z dot to A transpose Z plus C transpose V and N B transpose Z. Now here for this system we have to determine the controllability and observability. So for this system the state controllability for this system, the state controllability can be written as, so here, now here earlier if you see in checking the controllability we have taken B, AB, A raised to n minus B. So here the equation it is in terms of A transpose and C transpose. So here state controllability is starting with C transpose. So C transpose is nothing but the B of the original system. So here state controllability we can write down as C transpose A transpose C transpose, here A transpose C transpose. And now about observability. Now observability depend upon the C matrix, but now here C matrix is nothing but the B transpose. Therefore we can write observability as B AB, here to a raised to n minus 1 b. Now, we have got a state controllability equation like this and observability equation like this. This is for S2 plant, this plant. So, if you compare the state controllability for this system S1, so we will find that the state controllability equation for this S1 b a b a raised to n minus 1 b. So, for this plant this same equation will come here in terms of observability b a b a raised to n minus 1 b, that is controllability in S1 is nothing but the observability in S2, and similarly if you find that the observability here, this C transpose A transpose C transpose A transpose n minus 1 C transpose, it is similar to your state controllability, that is observability here it become the state controllability. Therefore, here we can say that the controllability and observabilities are dual of each other. All these controllability observability are very much important concepts. They are useful in applications, various applications. Now, here we are looking after the controller design. You will find that this for controller design it is the first step. Without controllability observability we cannot design a controller. So, along with this controllability observability has also very wide applications. It is useful in a Lyapunov stability analysis. It is useful in various model ordering techniques. Even we will find that this type of concept is also useful in image processing application also. But as our main purpose is to control design, so we will see further that how this controllability observability is helpful in designing of the controller. So, these are some references.